So I'm going to first evaluate f of x plus h. So I'm going to rewrite this function, and anytime there's an input, that becomes an empty parenthesis. And that empty parenthesis is filled with the input x plus h. And then if you simplify, x plus h to the second power is x squared plus 2xh plus h squared. And then distribute the 2. Now this expression can replace f of x plus h on the top left part of that difference quotient. And then we subtract f of x. So if you subtract an entire function, remember that has to be done in a parenthesis. Then if you distribute this minus sign, that becomes a negative 5, which cancels here, and this minus 2x cancels that positive 2x squared. So what we have left, oh, and that's divided by h. So what we have now for our difference quotient is a 4xh plus 2h squared divided by h. Now I'm going to factor out in the numerator just a single h. Even though you could factor out a 2h, the 2 is not going to cancel with anything down here. It's only an h in the denominator. So I'm just going to factor out an h in the numerator, leaving 4x plus 2h. So then the h cancels out, and we have 4x plus 2h. So for part A, when you find the inverse of a function, remember you switch the place of x and y. So it's going to be x equals 3 times y minus 1 cubed plus 5. Now to get y by itself, first step we're going to do is subtract 5. And then divide by this 3 right here, divide both sides by 3. Now to get rid of a power of 3, you use a cube root on both sides. And then the final step is to add 1 to both sides. So the inverse is that for part A. For part B, I'm going to switch the place of x and y. Now to get rid of this fraction, I'm going to multiply both sides by the denominator y minus 1. And to get rid of this parenthesis, because we want to get y by itself, and now it's inside of a parenthesis, so we can either distribute the x or divide it over here. So I'm going to divide the x. And then finally add the 1, and then that y is going to turn into the inverse of f. So the inverse of f is equal to 3 divided by x plus 1. So we're graphing a square root function that has a few transformations. So we have to the right 1 unit. Now remember, typically the square root function graph looks like this. That's just the square root of x. So we've got to decide where that beginning point 0, 0 is based on these transformations. Now, it may look a little more familiar to if I make one change. The negative 3 is going to stay as a coefficient. But instead of having that 2 at the beginning, I can put the positive 2 at the end. That may look a little more familiar to you that way. So now we have to the right 1 unit and up 2 units is where that starting value is. And then we have a vertical stretch and then a vertical reflection as well. So instead of the graph going up and to the right, it's going to go down and to the right. what I would suggest at this point, once you have that starting value, is plotting a few points for x that is near the beginning x value. Now we know it's not going to go this direction, so I'm not going to use any of this x values. I'm going to use x values here. So for example, when x equals 2, 2 subtract 1 is 1. The square root of 1 is 1. 1 times negative 3 is negative 3. Negative 3 plus 2 is negative 1. And then I'm going to choose to skip all the way over to 5. Reason being is we're doing like the square root, and 5 minus 1 is 4, and the square root of 4 is 2. 2 times negative 3 is negative 6. Negative 6 plus 2 is negative 4. So 5 comma negative 4. So it's got quite a big vertical stretch there. Okay, question 4, part A. We have f plus g of 2. And the other way of thinking about that is f of 2 plus g of 2. So all we need to do is plug 2 into both functions and then add together. So f of 2 is 3 times 2 squared minus 2. And then g of 2 is 2 times 2 plus 5. So we just need to add these two values together. So here we have 4 times 3 is 12 minus 2 is 10. And here we have 4 plus 5, which is 9. So this is equal to 19. For part B, f of g of x means that the g function goes inside of the f function. So if I rewrite f function with an empty parenthesis for the x value, then g of x is my input. So then we can replace g of x with 2x plus 5. So 2x plus 5 squared. I'm just going to write that up here. Remember, that's equal to 2x plus 5 multiplied by another 2x plus 5. When you distribute those together, you're going to get 4x squared. And then you're going to have a 10x and another 10x, so that's 20x, and then plus 25. So we have 3 times 4x squared plus 20x plus 25 minus 2. So that's 12x squared plus 60x plus 75 minus 2. So final answer, combining like terms, okay, question 5, part A, we're going to list the possible rational zeros using the rational zeros theorem. Remember, that's the p divided by q. So factors for the list of p come from that number, and factors for the list of q come from the leading coefficient 1. So p is plus or minus 1, 2, 4, 8, and 16. And then q, factors of q are just plus or minus 1. So if we combine those two lists into p divided by q, all the values of p divided by q is just plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So those are the possible rational zeros. Now for part B, we need to find all the zeros of the polynomial. So these are the list of possible zeros. So we're going to start with this using synthetic division. So if we start with positive 1, see if that works. So remember, this 1 drops down, multiply 1 times 1 is 1, and you add these together, so that makes 6. 1 times 6 is 6, 14 plus 6 is 20, 1 times 20 is 20, so it doesn't look like positive 1 works. So we can try negative 1. Okay, doesn't look like negative 1 works. Try 2. Okay, doesn't look like 2 is working. Try negative 2. Okay, looks like we got one there. Negative 2 is working. So this proves two things. It proves that negative 2 is a 0, which means x plus 2 is one of the factors. The other factor is x squared plus 3x plus 8. So a third degree polynomial should have 3 zeros. One of them is negative 2. This is going to give us another 2 zeros because it's quadratic. Sometimes this quadratic expression factors. Sometimes you have to use the quadratic formula. This time we have to use the quadratic formula. Two times 1. So 4 times 8, that's 32. 3 squared is 9. 9 minus 32. It's negative 23. And the square root of 23 doesn't simplify, but we have to take out that minus sign. So those are two complex or non-real zeros. So for part B, the zeros are x equals negative 2 and x equals negative 3 plus or minus I squared to 23 all over 2. Now for part C, it says to factor the polynomial into linear and irreducible quadratic factors, which actually is what we had right here. We have a linear and an irreducible quadratic. So for part C, we can list p of x as x plus 2 and x squared plus 3x plus 8. For question 6, we need to find a polynomial that has all of these characteristics. So degree 4 means it's going to have 4 factors that we're going to start with, and the zeros are going to tell us what those factors are. So first of all, p of x, if the 0 is x equals negative 2, then the factor is x plus 2, but if it has a multiplicity of 2, that means it repeats twice. And then remember, when you have a 0 that's complex like that, meaning it's got a non-real part, there has to be a pair, 1 minus I, so 1 plus I and 1 minus I. So we're going to get 2 more zeros, or 2 more factors rather, from those zeros. So what I suggested you do in class when you have a 0 that's complex like this is you subtract both the terms over. So subtract 1, subtract I. So the factor becomes x minus 1 minus I. And then with this one, you subtract 1 but add I. So you get x minus 1 plus I. I'd recommend you multiply these two factors together first. So x times x times negative 1, x times I, negative 1 times x, negative 1 times negative 1, and negative 1 times I, and negative I times x, negative I times negative 1, and negative I times positive I. So I can do that first. So x times x is x squared, x times negative 1 is negative x, and x times I is positive ix. Now start with this negative 1 times x is negative x, negative 1 times negative 1 is positive 1, and negative 1 times I is negative I. And then finally distribute this negative I to all three terms. So negative I times x is negative ix. Negative I times positive 1 is positive I. And negative I times positive I is negative I squared. So those two terms cancel out. Those two terms cancel out. Remember, I squared is negative 1. So this becomes minus negative 1, which is a positive 1, which we can add with that positive 1 to make positive 2. And then negative x and negative x combine to negative 2x, and then we have the x squared there. So now if we multiply those two together, we're going to get x squared plus 4x plus 4. And if we multiply those two together, so multiply this to that means x squared times x squared times negative 2x, and so on and so on. So if we multiply all those terms together, we're going to get an x to the 4th, and then a negative 2x cubed, and a positive 2x squared. And then the 4x multiplied by everything there is going to give 4x to the 3rd, and a minus 8x squared, and a positive 8x. And then finally, the 4 distributed to everything there is going to give a 4x squared, and a negative 8x, and a positive 8. And then when you combine like terms, we're going to get p of x equals x to the 4th. Now we have negative 2x cubed and 4x cubed, so that's a 2x cubed. And then we have a 2x squared, a negative 8x squared, and a 4x squared. So that's negative 6 plus 4 is negative 2, so we have negative 2x squared. And then we have 8x and a negative 8x, so those cancel out. And then a plus 8. Now, the last thing we have to consider is p of 0 has to equal 8. So if you plug 0 in for all the x, then there should just be an 8 left over, which is the case here. So it's degree, let's just check the zeros of x equals negative 2 with multiplicity 2, and then we have these two zeros. It's got degree 4, and p of 0, if all the x's are equal to 0, then we have an 8 left over. So looks like everything checks out. Okay, I'm going to start by factoring in the numerator and factoring in the denominator. So remember, the vertical asymptotes would be domain restrictions. Those come from domain restrictions in the denominator, which are going to be positive and negative 3. So we have a vertical asymptote at positive and negative 3. And it says show and label, so you have to have x equals negative 3 for that one, and x equals positive 3. The horizontal asymptote happens when we compare the degree of the numerator to the denominator. So if they're the same degree, remember you divide the leading coefficients. So this is degree 2, that's degree 2. They're the same degree, so we divide the leading coefficients. 1 divided by 1 is 1, so the horizontal asymptote is y equals 1. The x and y intercept, I'm going to find the y-intercept first, and I'm going to go back to the original form. So remember, the y-intercept is when x is equal to 0. So if all the x's are equal to 0, we have negative 1 divided by negative 9, which is 1/9. So 1/9 is right there, 0, 1/9. The x-intercepts are when y is equal to 0. So f of x is the same thing as y. So if this were 0, the only thing that's going to make a fraction equal to 0 is when the numerator is equal to 0. So really what we're solving is, if y is equal to 0, we need to find out what makes the numerator equal to 0. So we need to just solve this equation. It's going to be positive 1 and negative 1. So those are our two x-intercepts, positive 1 and negative 1. The domain for part D is x cannot be 3 or negative 3. So we're going to go from negative infinity to negative 3, and then from negative 3 to positive 3, and then from 3 to infinity. So this interval notation is all real numbers except for negative 3 and positive 3. Now we need to graph the function. So I'm going to start in the middle. You see we have 3 points already plotted. So it looks like there in the middle we have almost kind of like an upside down parabola. Now I'm going to go to the right side and just plot a couple of points. So if x equals 4, 4 squared is 16. I'm going to keep track of this on a table of values here. If x is equal to 4, we have 16 minus 1 in the numerator, so that's 15. In the denominator, we have 4 squared minus 9, so that's 16 minus 9, which is 7. 15 sevenths is about 2.1. So 4 comma 2.1. If we continue doing that for 5 and for 6, we'd get points that kind of look like that. So that tells us that that piece of the graph looks like that. And I'm going to do the same thing over there on the left side over here. So I'm going to plot negative 4, see what happens there. So negative 4 squared is 16 minus 1, that's positive 15. And then in the denominator, we have 4 squared, it's 16 minus 9, which is 7. So again, it's about 2.1. So negative 4 comma 2.1. And again, if we did 5 and 6, we'd get values that kind of look like that. Okay, question 8, part A. Solving a logarithm equation involves using a base on both sides, but we have to get this logarithm by itself. So I'm going to divide by 2. Now we can get rid of that logarithm using, in this case, a base 3. And then subtract 1. For part B, it's a problem when you have two different logarithms on the same side, or two logarithms on the same side of the equation. So we need to condense these into one logarithm. So this is going to be the quotient rule. Since there's a minus sign, so this is log base 9 of x plus 6 over x equals log base 9 of 2. So now, since we have a single logarithm on both sides, we can use a base of 9 to cancel each logarithm. We have x plus 6 divided by x equals 2. Now, like we've done before, if we want to solve an equation that involves a fraction, we can get rid of the fraction by multiplying both sides by x. And then subtract. So we have 6 is equal to x. For part A on number 9, we're going to separate this quotient first using the quotient rule. So quotient rule says we can separate using subtraction. So we're going to have log base 2 of x squared minus log base 2 of the denominator y cubed z squared. Now we've got to expand that product there, y cubed times z squared. So that's going to be the product rule. And when we're subtracting this expansion, you have to subtract the entire expansion in a parenthesis. So this is log base 2 of y cubed plus log base 2 of z squared. If you didn't include these parentheses, then all you would be subtracting is that first term. But you need to subtract the entire expansion because this entire logarithm is being subtracted, so this entire expansion has to be subtracted. Now the final step here is to move the exponents down in front. So the final answer here is 2 times log base 2 of x minus 3 times log base 2 of y. And you can also distribute the minus sign here if you don't want to have the parentheses. So then minus 2 log base 2 of z. For part B, we've got to condense all these into a single logarithm. Now, I don't particularly like how this is written, the whole logarithm being divided by 3, so I'm going to write that a little bit different. I'm going to write it as 1/3 times log of x plus 2. And now we're going to go backwards. Each of these coefficients are going to move back up as exponents. So this would be log of x plus 2 to the power of 1/3. And then x minus 1 squared. Now I'm going to condense these two logarithms using the product rule. So this is going to be x plus 2 to the 1/3 times x. And then I'm going to condense these using the product rule again. So these are all going to multiply. So one single logarithm, and then x plus 2 to the 1/3 is going to multiply x, and that's going to multiply x minus 1 squared. So they all form a product. Number 10, we're solving an exponential equation, which means we're going to cancel a base. In this case, we're going to have to use natural log. The only way to solve for a variable that's an exponent, remember, is to cancel the base. And natural log cancels a base e. So first we're going to add 2 to both sides and then divide by 2. So if we add 2 here, we're going to get 7. Then if we divide by 2, we're going to get 7/2. Now if we use a natural log to cancel the base e, we have the natural log of 7/2. Then if we add 1, we get x equals natural log of 7/2 plus 1. That's the exact form. Now the approximate form you could find on a calculator. And that would be 2.52. Since the denominator here only has 2 factors, then we're only going to have 2 partial fractions. Now, if we multiply this whole thing by the lowest common denominator, when it distributes over there, we would just be left with negative x plus 8. When it distributes over there, the x minus 2's cancel, So a multiplies with x plus 1, and then when this multiplies with the b partial fraction, the x plus 1s would cancel, so b multiplies with x minus 2. Now to solve for a and b respectively, the way this was described in class is by using convenient values. So if I want to solve for b, for example, then I want a to disappear, so x could be negative 1. So if we let x equal negative 1, then this is the opposite of negative 1, which is 1. 1 plus 8 is 9. Negative 1 plus 1 is 0, so a disappears. Negative 1 minus 2 is negative 3, so negative 3 times b means that b equals negative 3. Now if we want to do the same thing but to solve for a, that means b has to disappear. So in this case, I'm going to let x equal positive 2. The opposite of 2 is negative 2, plus 8 is 6. 2 plus 1 is 3. 3 times a is 3a. And then here b disappears. 2 subtract 2 is 0, so b is gone. So now we can solve for a equals 2. So now if we replace a for 2 and a b for negative 3, we have our two partial fractions. So it's 2 over x minus 2, and then plus negative 3 over x plus 1. Okay, we have the bottom row of this pile has 48 logs, then 45, and then 42, and then the final row has 24. How many logs are there total? Well, this is a partial sum, and we have to decide if it's the partial sum of an arithmetic or geometric. Looks like 48 to 45 to 42 is arithmetic. The common difference is negative 3, so the partial sum of an arithmetic sequence is n over 2 times the first term plus the last term. Now we know the first term is 48 and the last term is 24, but we don't know how many terms this is in total. So we don't know n. So we need to solve for n using the explicit formula of an arithmetic sequence. So the explicit formula is first term times n minus 1 times d. Now we know that d is negative 3, and we know that the first term is 48. So we can find this explicit formula as 48 plus n minus 1 times negative 3, rather, not negative 4, negative 3. So this is 48 minus 3n plus 3, so the nth term is negative 3n plus 51. Now, if I want to figure out what term this is, 24, then I can plug 24 in for a sub n and then solve for n. So I'm going to put 24 in there. If we subtract 51 on both sides, we're going to get negative 27 equals negative 3n. Divide by 3, we get n equals 9. So that means this is the 9th term where we're adding 9 terms. So this n turns into 9. So we have the sum is 9 terms divided by 2, with the first term is 48, the last term there is 24. So on a calculator, we get 324. Okay, so we're solving using the inverse of a matrix. They've already given us the inverse we're supposed to use. So the matrix equation I'm going to form a matrix of just the coefficients. And then we have the variables. And then we have these three constant values after the equal sign. So in order to get this xyz by itself, we have to cancel this matrix. The only way to cancel a matrix is to multiply it by the inverse. They gave us the inverse. So if I multiplied this to this, then remember this disappears, but then because this is an equation, whatever you do on one side, you got to do the other side. So we need to multiply this also to that. So that's what we need to show, this times this. And that will give us our solutions there. So this is a combination of that row and this column. So this is negative 21, positive 10, and 0. So negative 21 plus 10 plus 0 is negative 11. This answer is a combination of that row to that column. So this is negative 4 and 7, that's negative 28, plus 5, that's negative 23, plus 0, so negative 23. And then here we have this row to that column, so 1 times 7 is 7, plus 0, plus 0, so that's 7. So what we have is the XYZ matrix is equal to negative 11, negative 23, and 7. So the solution to the system of equations is negative 11, negative 23, and positive 7. Okay, for number 14, part A, we have a sequence. And they want the nth term. So the explicit formula for the nth term. So it really matters if this is geometric or arithmetic. So for 2 to negative 6 to 18 to negative 54, it looks like it's multiplied by negative 3. So that makes it geometric. The common ratio is negative 3. So the nth term formula, the explicit formula, is first term times r to the power of n minus 1. So the first term is 2. Common ratio is negative 3 to the power of n minus 1. For part B, the 10th term then would be a sub 10 to the power of 10 minus 1. So let me just figure that out on a calculator. And that's negative 39,366. So then for part C, an expression that could be used to find the sum of the first 10 terms. So the partial sum formula for a geometric sequence is first term times 1 minus r to the power of n So the sum here would be first term times 1 minus negative 3 to the 10th power times 1 minus negative 3. Now it says in part C, write an expression that could be used to find the sum of the first 10 terms. You do not need to calculate the sum, just set up an expression. So this is the expression we would use. I said you don't need to calculate it, just set up the expression. Okay, 15. So for this one, the question is not asking us to find the entire expansion of this binomial. This is from section 7.3. Typically, we would just multiply this and use Pascal's triangle to find every single term of the expansion. But they're only wanting one single term, y to the third. But we're still going to use Pascal's triangle. If this is raised to the 5th power, we need 6 rows. So this is the sixth row. Now remember, each of these is a coefficient for one of the terms of the expansion. The first, at the beginning of the term, at the beginning of the expansion, we're going to have this term raised to the fifth power. So this would be x to the fifth, some kind of a term with an x to the fifth, and y to the 0. The next term would have x to the fourth power and y to the first power. The next term over would have x to the third power and y squared. This term here would have x squared and y to the third. This term right here would have an x squared and y to the third. So this is the term we want, not because it has an x squared, but because it has a y to the third. So we're going to use this coefficient and then it's going to have that 3x to the second power and then the negative 4y to the third power. So this is just one single term of the expansion. There's the coefficient. It's 3x to the second power and negative 4y to the third power. Remember, the sum of these two is always equal to the original exponent. 3x to the second power is 9x squared, and then negative 4y raised to the third power is negative 64y cubed. So now we just need to multiply 10 times 9 times negative 64, and that is negative 5,760 with an x squared and a y to the third.